Okay, so welcome to this final lecture in this section. I'm Lars Hesselholt from Nagoya University and University of Copenhagen, and I will chair this session. The speaker is Peter Zograf. He received his Doctor of Science degree from the Leningrad Steklov Mathematical Institute, and he works at the Euler International Mathematical Institute in St. Petersburg. And the title of his talk is Counting Lattice Points in Moduli Spaces of Quadratic Differentials. Please begin your talk.
Thank you. So thank you for the introduction. And in my talk, I'm going to report on the recent progress done jointly with Vincent Delacroix, Elise Gujal, and Anton Zoric in counting lattice points in modular space of quadratic differentials. This count has some interesting applications that I'm also going to talk about somewhat later. So I would say that our work was inspired to a great extent by beautiful results and ideas of Maria Mirzakhani. Actually, she anticipated many things that we later came across ourselves. Another mention I found important is a nice work of Paul Norbury relating lattice point count in the modular space of curves to the intersection theory of the modular space. His results were rather important for us. So to begin with, let me remind some basic facts about modular spaces of quadratic differentials. A holomorphic or meromorphic quadratic differential Q on a smooth complex curve C of genus G is a holomorphic or meromorphic section of the square of the cotangent bundle to C. The modular space of quadratic differentials with n simple poles is this space of equivalent of isomorphism classes of pairs, a complex curve C, and a holomorphic section of the square of the cotangent bundle twisted by the divisor of the marked points. In other words, the modular space of quadratic differentials of genus G with n simple poles is isomorphic to the holomorphic cotangent bundle to the modular space of curves of genus G curves with n marked points. The space QGN is naturally stratified according to the sets of multiplicities of zeros of Q. A generic situation is when all zeros are simple. There are 4G minus 4 plus n simple zeros on a curve and we denote by Q of such a notation. Here 1 to the 4G minus 4 plus n is the number of zeros, and minus 1 to the n is the number of simple poles. We assume that both zeros and poles of Q are labeled, and then the principal stratum is a ramified cover of its image in the modular space QGN of degree for G minus 4 plus n factorial, and the image is open and dense in QGN. So we want now to introduce coordinates on the principal stratum in the modular space of quadratic differentials. It is done via a canonical twofold cover, that is a curve C hat that lives in the cotangent bundle to C, and here C x is a point in C, and omega of x is a co-vector such that its square is the quadratic differential. This cover ramified, that's a twofold cover that is ramified precisely over zeros and poles of Q. Over zeros, omega has double zeros, and it's regular at the inverse images of pole of Q. The curve C hat is smooth of genus for G minus 3 plus n, and omega is a holomorphic one form on C. Let us decompose the first homology group of C hat with complex coefficients into the sum of eigenspaces of the covering involution H1 plus and H1 minus, where H1 plus is the subspace even subspace, and H1 minus is an odd subspace in H1, in homology of C with complex coefficients. Let us now put H1 with superscript minus to be the group of odd homology classes on C hat. The period map is a map from the principal stratum in the modular space of quadratic differentials to the odd cohomology group of C hat with coefficients in C is defined by the following formula. That's for the pair CQ, that's the integral over the odd homology classes of C hat of the quadratic of the abelian differential holomorphic differential omega. This period map provides coordinates on Q on the modular space of quadratic differentials. The Masur-Veech volume form dV is the linear volume form on the cohomology group H1 minus, or the odd cohomology, odd subspace in the cohomology with complex coefficients of C hat. And it is normalized by the condition that the volume of the torus H1 minus over L is 1, where L is a lattice of linear maps from H1 minus to the group of Gaussian integers. The volume form induces volume forms on the level sets QGN at level A. That's a set of pairs CQ such that the area of C with respect to the metric defined by Q is equal to A. The area function is just the integral over the curve of the modulus of Q. That's a metric on C that is singular at the conical points at the singular, at the zeros and poles of Q. By definition, the volume of the principal stratum is the volume of the level set with area of 1/2, or it is the same, the volume of the disk bundle defined like this. So now I would like to establish a relationship, a correspondence between the lattice points, the points in the lattice L that was defined here, and the so-called square tile surfaces. The square tile surface is a connected oriented compact surface without boundary, built of squares of size 1/2 by 1/2. That's a quadrangulation of the surface with additional properties that each square has a pair of opposite sides called horizontal and another pair of opposite sides called vertical. So that horizontal sides are glued to horizontal ones and vertical sides are glued to vertical ones. A quadratic differential tz square on each square is compatible with gluing, and endos C with a complex structure and the meromorphic quadratic differential Q with its most simple poles. That can be seen on the picture here. This is a square tile surface with 3 conical singularities of angle 3 pi that correspond to simple zeros of Q, and 7 conical points of angle phi corresponding to the poles of Q. So that's how a square tile surface looks like. And an important fact is that there is a bijection between the set of square tile surfaces in the principal stratum and the lattice L in the first cohomology of C hat. In particular, we can compute the volumes by counting square tile surfaces in the principal stratum with at most 2n squares. The vertical bars mean the cardinality of this set, and the limit when n big tends to infinity is up to constant the volume of the principal stratum. This volume is usually called the Masur-Veech volume. Another important thing about square tile surfaces is that it admits a decomposition into maximal horizontal cylinders encoded by the waist curves of the cylinders and their heights. So on this picture, the first cylinder has circumference 6 and height 2. It is encoded by the symbol 2 gamma 1. The second cylinder has circumference 4 and height 1, and so on. Now, there is another object related to square tile surfaces. That's what is called the geodesic multicurves. We can end of C with the compatible hyperbolic metric with cusps at the poles of Q and the waist curves of cylinders form a geodesic multicurve gamma, written as the sum of gamma sub I hi, sum of I from 1 to k, where gamma I are simple closed geodesics and hi are the corresponding multiplicities. To each square tile surface or equivalent each multicurve, we associate its stable graph, gamma big of gamma. The stable graph is the collection of the following data. The vertices of it represent the components of the complement of the union of the irreducible components of the multicurve. Edges of gamma correspond to the curves to the irreducible components of the multicurve and connect the vertices representing the components of the complement to the union of irreducible components of the multicurve adjacent to gamma I. Gamma has also n legs or half edges labeled from 1 to n, where the ith leg is incident to the vertex that represents the component that contains the ith pole of Q. And at last, at each vertex, the stability condition is satisfied, where G of V is the genus assigned to V, and N is the and N of V is the degree of valency of the vertex V. The genus of a stable graph gamma is defined by this formula, where V of G is the set of vertices of gamma, and V1 of G is the first dirty number of the graph gamma. So on this picture, all the multicurve and the corresponding stable graph, all labels are at vertices are equal to 1. There are 4 edges and 7 legs. For a pair of non-negative integers g and n, with the condition that 2g minus 2 plus n is larger than 0, denote by gn the set of isomorphism classes of stable graphs of genus G with n legs. For a stable graph gamma in Gn, consider the subset of square tile surfaces with at most 2n squares, having gamma as the associated stable graph and h as the set of heights of the cylinders. Its contribution to the volume of the principal stratum is given by the limit when n tends to infinity of the number of square tiled surfaces with the associated graph, stable graph gamma, and the set of heights h, built of at most 2n squares. Here d is equal to 6g minus 6 plus 2n is the dimension of the modular space of quadratic differentials. This limit exists, is positive, and the volume can be written as the sum over all stable graphs the sum of the set of heights of the volume contributions of each stable graph. Here, E of G is the number of edges of gamma. Now, the first application of this correspondence between lattice points, square tile surfaces, geodesic multicurves, and stable graphs allows to deduce the formula for Masur-Veech volumes of the modular spaces. For that, we need to introduce certain polynomials and Gn of variables v1 to vn that are given by this formula. Here, the integral over the Deligne-Mumford modular space MGN of the psi classes, and this is a well-known object. The generating function of these numbers, of these intersection numbers, is the famous object introduced by Witten, who conjectured that this generating function satisfies the hierarchy of Korteweg-de Vries equations. This conjecture was proven by Kontsevich and then by many other people, and these numbers, they are relatively well studied, and they appear as top degree coefficient in the lattice point count polynomial of Paul Norbury. So, yes, psi1 to psi-n are the tautological classes on the Deligne-Mumford modular space, and the sum of these should be equal to the dimension of MGN. Now consider the linear operator YH defined on monomials by this formula and extended to arbitrary polynomials in V1 to Bk by linearity. For a stable graph gamma with vertex set V of gamma and the edge set E of gamma, associate a homogeneous polynomial P gamma of degree 6g minus 6 plus 2 by the formula. By this formula, it's up to a certain coefficient given by the product over all edges. To each edge, we assign a variable BE times the product over all vertices, and to each vertex, we assign the polynomial NGN that was just defined, where B bold denotes the set of variables assigned to half edges. We assign a variable to a half edge of a full edge, and we assign 0 to a leg. So, in terms of this polynomial, the Masur-Veech volume of the principal stratum is given by the formula. The sum over all stable graphs of genus G with n legs. So n edges. Overall, the sum over all sets of heights of the operator YH applied to the polynomial P gamma. So this formula has some advantages, namely it gives the volume as the sum of individual contributions over stable graphs. But on the other hand, the number of stable graphs grows rapidly with G and N, and it's not very well suited for computing these volumes. There is an alternative approach to volumes of modular space of quadratic differentials that is due to Chen, Muller, and Sauvaget. They derived a quite different formula for these volumes using intersection theory on the modular space of quadratic differentials, and they express these volumes in terms of the so-called linear Hodge integrals over the modular space of curves. What is interesting that both formulas give the same values for the volumes, but at least I don't know of any direct proof that these two formulas are the same, give the same things. Now, another application is to the statistical geometry of random multicurves. So let's see the hyperbolic surface of genus G with n cusps. And let gamma be a multicurve on C consisting of pairwise disjoint primitive simple closed geodesics gamma I. Denote by L the hyperbolic length function and put L big equal the sum over irreducible components gamma I of lengths multiplied by multiplicities. So this L is called the total length of the multicurve gamma. Now denote by MLGN of Z the set of integer points in the space of measured laminations. On C, two multicurves have the same topological type if they belong to the same orbit of the mapping class group in the space of integer points and on the set of integer points in the space of measured laminations. By definition, the asymptotic probability that a random multicurve belongs to the orbit of the modular group mod Gn is the limit of the ratio of the number of multicurves in the orbit of gamma that is not longer than L over the number of all multicurves whose length doesn't exceed L. The following formula is a refinement of a result of Mirza-Hani and describes this probability in terms of the volume contribution of stable graphs. Namely, the asymptotic probability Pgn of gamma is given by the ratio of the volume contribution from the stable graph gamma with the set of heights h over the volume of the total stratum of homomorphic quadratic differentials. Here, as I said, gamma is the stable graph corresponding to the multicurve gamma. For n equal 0 and g is greater or equal to 2, there is a single topological type of non-separating simple closed curves, closed geodesics, gamma 0, as in figure 3, and the integer part of g over 2 topological types of separating closed geodesics, as in figure 4, where gamma I cuts the complex curve into parts of genera I and G minus I respectively. So let me show the pictures. So on the left, there is a complex curve with a non-separating geodesic gamma naught. And on the right, there is a corresponding stable graph. So it has one vertex, one edge, and the vertex is labeled by G minus 1. That's the non-separating curve. And for separating curve, we have on the left the picture of a complex curve with a separating closed geodesic, and on the right the corresponding stable graph. It has two vertices and one edge. The vertices are labeled by numbers 1 and G minus 1. So these stable graphs are quite simple, and it's possible to compute their contribution to the volumes directly. And this computation gives the corollary that the sum of probabilities that a curve separates, that a geodesic separates a complex curve over the probability that this geodesic does not separate the curve is given by this expression. So we see that for large G, the probability that a random closed geodesic is non-separating is exponentially more frequent than separating ones. I would also like to say that this result was generalized to multicurves on large genus, and it's discussed in detail in our paper with Delacroix, Gouchard, and Zograf. Now let's go to the third application of the lattice point count, namely to the enumeration of meanders. A meander is a configuration in the plane that consists of a straight line and a simple closed curve transversely intersecting it, considered up to isotopy. Enumeration of meanders is a long-standing difficult combinatorial problem. So here on this picture, On the left, you can see a meander with 10 crossings. Let M of n be the number of meanders with 2 crossings. Conjecturally, this number behaves like this. But up to some constant, it has an exponential factor, r to the n, and polynomial factor, n to the alpha, as n tends to infinity. So what is known? These numbers m of n were computed up to n equal to 28, I think. But there is a plausible prediction for the power alpha that comes from interpreting the meanders as a conformal field theory that is due to differentials co-authors. But there is no guess even on the conjectural level what is this number r. So there are not so much is known about how this number of meanders behaves for large n. The situation becomes more tractable if one imposes additional topological conditions. An arc is called minimal if it connects two adjacent intersections of a meander. The maximal arc connecting the first and the last intersection, if present, is treated as a minimal arc as well. Denoted by m sub n of n big, the number of meanders with 2 uncrossings and n minimal arcs. So let's go back to the picture. So on the left there is a meander with 10 crossings and 6 minimal arcs. There are 5 of them that are 1, 2, 3, 4, 5 minimal arcs that are finite, and there is one minimal arc at infinity. So that's the arc number 6. And it's not hard to see that meanders correspond to certain square tile surfaces. So on the right, you see a square tile surface that corresponds to the meander at the left. That's a meander is a 4 regular graph. So what we have on the right is a dual graph to the meander, and the arcs with arrows, they show which pairs of sides are glued together. This square tile surface is very special in the sense that there is only one horizontal cylinder of height 1 and maximum circumference, and if we make all the gluings, we can see that there is also precisely one vertical cylinder of width 1 and circumference, maximal circumference 2n. So there is correspondence to each meander with 2n crossings and then minimal arcs. We associated genus 0 square tile surface made up of 2n squares with one horizontal and one vertical cylinders of maximal circumference with n simple poles and the marked point. We need now to mark a point that corresponds to the point at infinity of a meander. And this correspondence is generically 2 to 1 for large n. So now let's consider 3 nested sets of square tile surfaces. One is the set of all square tile surfaces in the principal stratum, built of no more than 2n squares. The second one is the set of all square tile surfaces with precisely one horizontal cylinder of maximal circumference, built of not more than 2n squares. And the last set is the set of square tile surfaces with one horizontal and one vertical cylinders, again built of no more than 2n squares. So these set cardinalities of these sets behave like this. It's given by these 3 formulas. Here, G is the dimension of the modular space of quadratic differentials. And in particular, we have the following formulas. The following formula for the number of meanders with 2n crossings and minimal arcs. Its asymptotic is given essentially by the constant C11. We cannot access this constant directly, but we can do that in an indirect way. We can evaluate the constant C of n and C1 of n. C of n is just the Masur-Veech volume of the principal stratum in the space of quadratic differentials of genus 0 and n simple poles. This formula was obtained by Atreya, Eskin, and Zograf. The coefficient C1 of n can be computed by direct combinatorial consideration, and it's just a binomial coefficient. And at last, these 2 ratios, C11 over C1 and C1 over C, are equal. That follows from asymptotic, from the fact that the numbers of horizontal and vertical cylinders, the horizontal and vertical decompositions, are asymptotically independent. As a conclusion of this formula, we get the following statement. We just express C11 as C1 squared over Cn and substitute the formulas for them, and we get the following expression for the number of meanders with a fixed number of minimal arcs. That is indicated here. So it behaves polynomially as n to n minus 5. That's the leading term. But there is no information about the subleading term. How can it be? So these techniques are also applicable to asymptotic enumeration of pairs of transversal multicurves on surfaces of arbitrary genus, satisfying certain topological restriction. And that is done in our joint paper with Zograf, Gujar, and Zograf. It's hopefully will appear soon. So here I'll stop. Thank you for your attention.
Thank you for your lecture. We do not have time for, or it's not possible to ask questions here, but if somebody has questions, please email Peter.